In the previous videos, we wrote scripts that let us calculate the root of a given function. The methods that we used were the recent ones that were the bisection method, the regular falsy method or the false position method, and the recent one which was the secant method. So in this video I am going to show how we can write those scripts as functions. The advantage of using functions is that they can be recycled. So the function that you write for each of these methods can be used by you in different scripts. Currently these methods that I have written, they are written as scripts. They are written in a file which you can use. But let us say you are solving a problem. You are solving a problem in which you are required to figure out the root of the function. So think that I mean, just imagine that finding the root of that function is just a part of the problem. So in your entire script, the root finding is just a small part of the given problem. So instead of rewriting the whole code, it would be better if you had a function somewhere which you could just call into your script, and that calculates the root for you. So we'll see how we write functions in Octave. To make more sense of this video, it would be better if you had watched the previous 3 videos on root finding, which were on bisection method, regular falsy method, and the secant method. So let's begin the functions. Let's begin how we can write functions in Octave. So before that, let me make a folder in which I'll be storing my functions. Let me just call them my functions. Okay, I'll be storing my functions in this folder with the name my functions. So let me write the first function, which is bisection.m. So remember, when we write functions in MATLAB or Octave, this is the syntax that you have to follow. You have to start with the keyword function. Then you have to write the values which you want your function to return. You have to write the name of the variables which you want your function to return. So what I want is the root value, right? So I always denote it with C, as you can verify from our previous discussions. Let me just check if it is recording. Yeah. So the values that I want my function to return is C and the number of iterations. So I'm going to call these two variables C and iterations. The other thing that you have to keep in mind is that when you're writing a function in MATLAB or Octave, the name of the function should be same as the name of the file. So the name of the file which I have given is bisection, so my name of the function will also be bisection. Then you have to write the parameters which the function takes, right? For example, in mathematics you write f of x, you pass x to the function f of x and you get some output y. So this is similar to your f of x. This is bisection of, in place of x we'll be writing the parameters that the function bisection takes. So the parameters that a function that the bisection function takes, or it should take, is, as you can already tell, or you would already know if you had seen the previous videos, the first parameter is the function itself, the function whose root we are we want to find. So that function, it takes in the value of the interval a comma b, and it takes in the tolerance value. Tolerance means how close to the actual root we want to get. So that is defined by the tolerance value, and then we end the function. So these two keywords are necessary. A function file starts with the keyword function and ends with the keyword end. Now we write the body of the function. So for bisection method, what goes in? So before that, since I'll also be counting the number of times the while loop runs, I'm going to use a variable to do that for me, and I'm going to initialize the variable. So initially, when the loop hasn't even run one time, the value of that iteration variable or iter is 0. As the loop starts running, we'll update it by 1 each time the loop runs. So now, before starting the loop, let me calculate the value of the assumed root, which we assume it to be in the center of the interval. So instead of writing a plus b by 2, I can use a MATLAB function itself for that. The function is mean, and it finds the mean of a vector passed to it. So the vector that I pass to it is a comma b. This is same as a plus b by 2, but now we are making use of MATLAB's own function. Now let me write the loop. So I check the absolute value of the function at c, At each iteration I check if it is greater than tolerance. If it is, then I run the function. Alright, what do we do now? If you again recall, in bisection method we check if the value of c that we have got, we check the interval. We want to figure out in which interval the next value of root will lie, or see, now we have three intervals, right? A, B and B, C. So we want to check on which interval the root lies, and the way we do that is by multiplying the function at A, B and at B, at A, C and at B and C. So again, if you look at the previous lectures, this part will be clear to you. So wouldn't it be better if I had another function? Let me call that function root interval. If I pass the value, the function, then A, B and C, if I pass these values to this function called root interval, it should return me the interval in which the root lies. So that would be better, right? And why am I writing a separate function for this? Because we need this particular function, the function which finds the root interval for me in bisection method as well as in the regular falsy method or the false position method. In both these functions we need to figure out the root interval, or the interval in which the root lies in each iteration of the while loop. So it's better that we have a separate function dedicated just for doing this. So even though we have not written this root interval function yet, let me just implement it here. I'll write it later. So let us assume that we have we have a function called root interval, to which if we pass these parameters, which are the function, the value of A, B and C, it returns the interval in which the root lies. How that works, we'll look at it later. Alright. And now once we have our interval, what do? We calculate the value of C again, which lies in the center of this new interval. And then I update my iteration variable once, and that's it. We are done with our function called bisection. Let me open up Octave and let me define a function. Again, same function, log of x minus, you can always play around with different functions. Okay, this is not how you define, I need at the rate. Okay, so now I have my function defined as such. Let me call my own function which I made, which I call bisection. Remember what it takes. What does it take? It takes in the value of the function, it takes in the initial interval, so let it be 1 comma 3, and it takes in the tolerance value, so 1 into 10 to the power minus 6. So if I pass these values to bisection method, it'll return two values which I'm going to store in C and iter, or let me call it n, right? I can name these variables anything I want. So I'm calling my own function which I have just written now, with the function, the interval and the tolerance value, and I'm going to store the returned values in C and n. C is the root, n is the number of iterations. Okay, so what's the mistake? It says error, root interval undefined. So let's get back to this bisection. See, this root interval, I assumed that it returns the correct interval in which the root lies, but I have not yet implemented it. So let us implement the root interval function. Let me exit Octave. Let me write a function which calculates this root interval. Interval, fine. So remember the rules for writing a function. It should start with the keyword function. Whatever it returns, I write it here, and the name of the function should be same as the name of the file. So the name of the file was root interval, so the name of the function is also root interval. What does it take? It takes in the function value of A, B and C. How does this work? So you already know what the logic behind this. So I check if the value of A times the function's value at C, if it is less than 0, that means the root lies within this interval. So what I do is I make B equals C. If it does not, then A equals C, right? So that is all you have to do, and done. So now you have implemented. To understand this in more detail, again please look at the video on bisection method. Fine. Now my code should work because I have this root interval function defined. So let me define f first, and then let me call bisection method. So yeah, so now you can look, the value of the root is 1.4296 and the number of iterations it took is 20. So this is one of the functions that we defined. Let me define another function which was the regular falsy. So let me call it vim regular false position. Let me call it false position dot m. The rules remain the same. Start with the keyword function, store the outputs in C iter, name the function same as the name of the file, pass in the parameters, end it with the keyword end, initialize the number of iterations as 0, and yeah, in false position, remember how we calculate the value of C. It is the point where the line joining the function at A and line joining the points of the value of the function at A and the value of the function at B. So the line where it crosses the x-axis, that's the point we take as C. And the formula we derived for it in the false position method video is A times f of B minus B times f of A divided by f of B minus f of A, right? And now we start our loop. It checks the absolute value of f of C, checks if it is greater than tolerance. If it is, it runs the loop. In the loop, what it does is it checks if it checks in which interval the root lies. We already have a function for that, which is called root interval. I'm going to call it again here. See the advantage? Now I don't need to implement this twice. I can simply call this root interval here also. The values I pass, the parameters I pass to it, the arguments I give to it is f, a, comma, b, comma, c, and then I calculate the value of c again, right? And I need to do one more thing, which is update the iteration count by 1, and I'm done. Wait, it would be better if I can, in fact I should end it with a semicolon to suppress the output, and I'm done with the second function as well. So again, let me define f, let me call bisection method, and now let me call false position method with the same parameters, right? So I get the same value of root, but the number of iterations is 10. What else is left? If you remember, the third one, these are bracketing methods. The third one is secant. So let me write a function for that as well. Again, exit, name it secant dot m. Remember the rules: function keyword, store it in C iter, name the function same as the name of the file, takes in f, comma, a, comma, b, comma, tol, which is the tolerance, end it with the keyword end, then initialize your iteration count, calculate so calculate the value of c, which is, let me just copy it from the previous one. It was in the false position, right? Let me just copy this line, let me paste it here. All right, let me close this. Fine. So I calculate the c as I did in the false position method. In both the places the calculation of c remains the same. So let me start my while loop. It checks the absolute value of the function at c. It checks if it is greater than the tolerance, and then what it does inside is now this one doesn't look for the interval in which the root lies. It simply updates the value of b to, so ab is defined earlier and we get c, so now b gets updated to a and b gets, so a gets updated to b and b gets updated to c, and then I calculate the value of c again. Excuse me. Okay, fine. And now I need to update my iteration count by 1, and this should do. Let me open up Octave again. Let me define the function. Let me call the bisection method first. I get the root as 1.4296 in 20 iterations. Let me call the false position method. I get the same value of root 1.4296 in 10 iterations. Let me call now the secant method. I get the same value of root 1.4296 but only in 6 iterations. So I hope you can see how defining this function is really useful, because now you can call them anywhere in your code. You can call these functions and they'll do the job for you. You don't need to understand. So if for someone who is using your code, they do not need to understand what's exactly happening in each of these functions, bisection, false position or secant. All they need to know is how to use this function. The way you use this function is by defining, by giving its arguments as the function, the value of the interval a, b, and the tolerance that you want your root to achieve. Right? So this is how you define functions in Octave. Right? One last trick, if you want. So for example, if I exit this now and I close it and I open up again Octave, let me increase the font size. If I open up Octave again and if I try to access, let me define f, let me call that. Now if I try to run this function, this will not work, because this function will only work if I am in the folder where I have written this function. Currently I am in the folder home Divya Prakash, but my function, it's in this folder. I need to go to that folder. Let me go to graduate computations, my functions. This is where my function lies. Now that I am in this folder, if I run this command, it will work. But if I go back 2 folders back, you can do pwd, which is present working directory. This is a command which prints your present working directory or the present folder you are in. So currently again I'm back to my home folder, home Divya Prakash folder. If I run this function again, it will not work. But is there a way to make this work irrespective of the folder that you are in? There is. So what you do, you go to that folder where your functions are. You run this command called add path, and in the argument you give it present working directory. So what it does is, okay, whenever you enter any command in MATLAB, it goes to the folders which are defined in a variable called path. For example, if I run plot or 1,1, how does it know what thing to run? So it goes, Octave checks a variable called path which has the locations of all the directories which contain these functions. Now you want your directory which have your functions, you also want them to be added to this path variable where Octave looks for the commands. You can do that using, so the first thing that you do is you go to your folder, then you run this command called add path, and you ask this command to add the path of your current folder which is given, or either you can type this entire thing or you can just write pwd. You can ask it to add that path to this to the place where Octave will look for functions. Once you do that, you do save path, and now your program should work. So let me exit it, let me restart it again just to show you how, just to show you that it really works. Let me open up Octave. Okay, Octave, and again define the function, and now see where I'm in the home directory. Earlier it wasn't working, the function wasn't working, but now it will. Let me run my function secant, and as you can see, this works. So all the functions that I defined in my functions folder will work. This also works, and this also works. So this is how you can get your function to run from any place you are in the file system. So thank you for watching. I'll see you in the next one.